edge of the computer scientist we talk with, in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，你比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。我觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科。even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the level, at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。 数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。
So we are at a moment where I think the computational power, it's really at the maximal level, maybe a bit better, but nothing exceptional. It's not going to be like 1,000 times better. And but mathematically, as I say, there are many challenges, and I think once we will understand better how AI works, why it works, how to improve it, how to make it more efficient, safer, and everything, this is when we will see a next revolution.
I mean, if you have theory but without practical case, so you find, you kind of lose a sense of purpose. Whereas, here, if you do also the practice but without a good theory, well, you will continue on improving already known techniques, but you will not do something revolutionary. I mean, of course, you will advance the technology, but basically you will be in the same trend. I mean, we'll just add some new layer of refinement, but it will not be a step forward somehow.
So we think that, of course, when you are a theoretician, you are looking for understanding. But when you are an engineer, you are looking for something which works better. But then there is a miracle that usually when you get better understanding, you become more efficient. So here what we need is in some sense to enrich the amount of mathematical knowledge of the computer scientists we talk with in order to make them realize that they can try to implement larger schemes.
就比如说是像那个大型语言模型，它里面最基础的模块是 transformer。transformer 实际上基本来说90%以上都是矩阵运算。这些矩阵运算我们如何给它加速？如果说我们能够加进很多数学的东西，就比如说利用好的矩阵分解、张量分解，利用比较好的核函数的设计，以及利用比较好的那个位置编码的方式，我相信是可以更有效的去加速整个大型语言模型的计算。
I studied mathematics. I developed new methods for solar physics. And then during conferences, I met people from cardiology. They showed their time series, their measurements, and looked very similar as solar activity. And then this is a way of interdisciplinary. Then we talked with each other and worked with each other. But the important point is each discipline has its own language, specific language. And the problem is that you have to learn, each side has to learn a bit the basic parts, not complete, but basic parts of the language of the others, that we really can communicate and that they can tell what are their real problems.
比如说可以从黄大年开始，你比如黄大年可以提供一系列的数学的课程，比如说是一些跟那个 AI 相关的数学，或者说跟其他方面，跟研究物理、跟材料、化学都需要不同的数学。从最简单的方程式开始，慢慢一步步的把这个问题给解剖开来，往深的方向走，就看你的兴趣。觉得要有一个好的一个提供知识的平台，我觉得需要形成一个这样的机制。数学是最赤裸裸的东西，它直接告诉你一个事情的一个现象的本质，背后的本质是什么。
And mathematics is really something that once you understand it, you can see the beauty of it. You can see the kind of creativity. For some things it's like art. If we think about everything which surrounds us, the technology, the laws of physics that describe what happens in nature, we can use them, we can do something with them. We have the technology that we have because there is mathematics. Mathematics has been the way for the human to understand phenomena.
That in fact, by now there are in fact many parts of mathematics which have become interesting for applications. So many more than a few decades ago.
应用往往是一门综合学科 ，even 在数学里面，你要解决一个应用数学解决问题，你不是一个单门的理论数学可以解决，这实际上是一个系统工程，数学的系统工程。Okay, today's theme is math for AI. Sorry. Okay, how math reshapes AI? Okay, okay. Once again. Hello everyone. Today's theme is how math reshapes AI. I have prepared a few questions for our speakers. Sorry. No. Once again. 这直播啊，已经开始了。Okay. Today's theme is how math reshapes AI. And I prepared some questions. The first question is to Laurent Lafforgue. It's about explainability. You know, explainability is a crucial issue in the academic community, and solving the problem requires quantitative characterizing the mathematical relationship between the structure and performance of a deep neural network. Although providing an exact description and measurement of the relationship might be difficult, but is it possible to approximate this relationship? For example, if we consider a certain performance measure for a deep neural network as a function of the network structure, can we determine the upper and at least the upper and lower bounds of that function? And such theoretical tools will not only help us understand the mechanism of deep learning and evaluate its generalization performance, but also providing guidance for designing deep networks. Could you please share if there has been any related research in this direction?
So I think AI has developed quite quickly in recent years on the basis of, as far as I know, of very simple mathematical principles. So in fact, it is just incredible that so much can be obtained with such simple principles. So I am thinking about, in particular, about the idea to construct functions by composition. So this idea for mathematicians is extremely elementary. Already in high school, students or pupils are familiar with that. And at some point, some people realized that it is much more efficient to construct approximations of data by composing elementary functions rather than by taking linear combinations of prescribed basis functions as was done before. So the people just realize that, and it happens to be very successful, much more efficient, but it seems to me that we don't really understand why. And of course, this situation is quite annoying for mathematicians, in particular for me, because mathematicians mainly aim to understand. And so we would want to understand more, but it is not only a question of curiosity, it is also because by experience we know that when we understand better, we are able to design more efficient systems. I think that at the present moment, AI is mainly something created by engineers using very simple mathematical principles, and it is waiting for more understanding, which it seems to me necessarily requires mathematics. And when I say that, I think in particular about deep learning, the idea of neural networks. So it is efficient, but why? And is it possible to build a mathematical theory of that which would explain and which would also make us able to predict what is more efficient and what is less efficient? In some sense, we are in a situation where mathematics is, you see, did not come first. But in fact, it is not the first time in history that we have a situation like that. For instance, of course, in the present state of science, even of mathematics, statistics is very important. But statistics began to appear in the 17th or 18th century. First, because people wanted to understand a little better, or just to get information on the modern societies which appeared at this time. In the 19th century, it began to touch biology. Then, in the late 19th century, to touch physics with the creation of statistical physics as a way to explain thermodynamics. And it allowed the creation a little later of quantum mechanics. But statistics as part of mathematics was the last thing, the last step in this process. So statistics was developed by other people well before mathematicians came in. And in fact, we are in a situation which is a little similar to that. But of course, when statistics became part of mathematics and it merged with probability theory, it was formalized, in particular by the Russian or Soviet school with Kolmogorov and other people, then it became much more powerful. And so I am expecting that something like that will happen.
Yes, nowadays statistical physics is still the main supporting factor for nowadays machine learning and AI. In the past years, we had only some parameter like width and depth of a neural network, but nowadays we have a more advanced theories about VC dimension, regularization, and information theory and optimization. But still, I think explainability, we are just at the beginning. Any different view or any view to add?
What I believe is that there is something which is not understood, in fact, as Laurent said, about why the structure, for example, a transformer or a deep net is so powerful. And also what is clear is that there is a classical theory, I would say, of complexity, regularization, and this which is based on VC dimension, or which is based on Rademacher entropy, and all this quantity which measures the quantity of information or the complexity of the function class which is trying to approximate. And we have all this nice theory which has been developed by Vapnik and others, and all this theory completely failed in the case of neural nets. So I think it means that there is a theory of machine learning and function approximation and stat, but this theory is not able to cover what we are really seeing in practice. Okay, so for example, it's not we cannot predict why transformers, and it's very, very unexpected why transformers are so powerful, why transformers are so universal also, because they can handle text, images, or and it's to me it comes as a surprise. So I think, of course, MLP, so classical multilayer perceptron, we start to have a kind of understanding why multilayer perceptron might be powerful, why convolutional net can be powerful. There are some theories saying that that it preserves some kind of invariance, but there are even now there are much more sophisticated structures, like say for example transformers, which are very, very sophisticated, which are extremely powerful in practice, and the classical theory of functional approximation does not is not able to capture that. So typically, the classical theory would say that it is impossible to learn. For example, yesterday I was mentioning generative models. So the classical theory of statistics says that it is impossible to learn in large dimension. It's impossible to learn a density, for example. And in practice, when you do generative model, you are not estimating a density, but you are sampling from some density, which is, with the current theory, would say we have more impossibility results than clear explanation. So there is something that we don't understand, I agree. And I agree that with Laurent, that math is really, really well behind what we achieve. So we don't understand what we are doing. And it gives, of course, it's a bit frustrating because it's difficult to predict why, which algorithm will be powerful and which algorithm, and even, for example, to cite LLM, so people, nobody was believing that an autoregressive model was capable to generate, for example, a text, a very long text, with some kind of coherence, and whereas the generation is purely autoregressive, so it comes as a surprise. So I think yes, we are as I said often, we are constructing we are like Denis Papin, so we are constructing a machine, but we don't understand thermodynamics. So it's like we are in the process, so we know how to do it. It's like really engineers know how to develop algorithms which are very powerful, and the theory that we have is lagging, behind a lot.
Maybe a couple of thoughts I can add. We had architectures that were perhaps more amenable to interpretation, like random trees and random forests, where you can really explain what the prediction is, but they just perform poorly compared to neural networks. So they are more explainable, but the explanations somehow don't seem to be the right ones. So another thing perhaps to mention is that in some cases you need a huge network to train, but then once it's trained you could compress it a bit to something much smaller that could be some kind of explanation. And I think it's an interesting phenomenon that you need to go big to train, and then you can have a crisper representation, and this could lead to some form of interpretation. So maybe network compression is a way to get some form of interpretation. So ideally, the compression preserves the input-output relationship of the network. So now you are happy because you have something simple that might be seen as an explanation that is describing the input-output relationship. But even if the compression is not so good, I mean, this could be a way to have, semi-plausible explanations, starting from a big performing network, compressing it to something a bit less performant, but at least interpretable somehow.
Yeah, compression is a big topic. There are tons of methods of compression, but if we can, for example, think about a hybrid model, because normally the last layer is linear, becoming linear, and the linear is more easy to explain, and we can hide the nonlinear processing in the middle, right? We need both the flexibility and of non-linearity as well as the explainability of linearity. My next question is again first to Laurent, is go further. Is about universal approximation theorem, and why deep learning why is deep learning capable of achieving such astounding results across various fields? This might be attributed to so-called universal approximation theorem, which we discussed just now. But however, if we delve into the way deep learning approximates, we find that it differs greatly from classical mathematics. In classical mathematics, at least in the machine learning age, the technique like a Taylor expansion, Fourier series, provides a clear, interpretable ways to approximate functions. For example, increasing the degree of polynomials or introducing higher frequency functions. And these approximations are additive, linear, for example, in the Hilbert space. So while deep learning approximates more complex function, it's not additive. It's a complex function by increasing the number of layers and creating composite function, which makes it very hard to interpret. Is it possible to draw from classical mathematical ideas on function approximation to design deep neural networks that have innate interpretability?
Yeah, difficult question once again. So of course it touches to most important theme of mathematics, which is a theme of approximation. Here, so what you are just recalling is that at least there is a theorem which tells us that by composing, for instance, linear functions with varying coefficients, alternatively with fixed nonlinear functions of this or that type, you may approximate, for instance, all continuous functions. So there is a theorem which tells us this. So this is an element of explainability after all. But what is not explained at all is why this process is much more efficient than the process, for instance, that you have recalled, for instance, Taylor expansion, Fourier series expansion, so which are all instances of taking linear combinations of prescribed functions. And so okay, so it is difficult for me to provide an answer because we don't have an answer at the present moment. But I would expect that as in other histories of the past, explanations will come from elsewhere. So, for instance, Éric Moulines took the comparison with the Papin machine, which later, whose functioning was later explained was thermodynamics, and thermodynamics was explained by statistical physics. But you see, statistics did not come at all from trying to understand these machines. It came, once again, it began in the 17th century, so for instance with Blaise Pascal, who was just looking at people making tries with dices or things like that, so taking chances and okay, so and in fact this is typical of what happens in mathematics. So mathematics is a word to abstract, and abstract means that starting from a situation you progressively understand some basic structures which grow out of this situation, and by abstracting them, you become able to carry them to other domains, which maybe can be very far away. So I think, for instance, that in this situation where we are confronted with the phenomenon of the success of deep learning, which we don't understand, maybe the explanations will not come directly from trying to understand the existing systems. I think it is, or maybe we can, of course, some people try to at least to get a little more understanding. This is very good, but I also expect that explanations will come from different directions. And so, for instance, as far as I am concerned, I am not so much interested in making progress on existing forms of AI. I am more interested in trying to develop, together with other people, other forms of AI based on completely different principles. Except, of course, that we need to retain some basic features, for instance, the idea of composition. And for me, as a mathematician, the science of compositions has a name. It is category theory. And I also think that this idea of approximation is extremely important. It is fascinating. It is at the very basis of all machine implementations. In fact, it is striking for me, for instance, listening to the different talks we had in the present conference. So people are talking about functions, about real numbers, about functions with real value and as if they were concrete. But in fact, this is not concrete at all. It is just usual. But in fact, it is extremely abstract. And if you want to, for instance, your computer to store real numbers, it is just not possible. Then, if you try to do this, you realize that real numbers are too abstract to become to be stored. It is just an idea. But what you can do with a computer is approximation. And so here comes the theme of the relationship between idealized notions, which in fact exist only in our mind, and their approximation by data which can be stored and processed by machines. And here again, for this, I am interested in pursuing this relationship through the mathematical theory, which is of the greatest interest for me presently, which is Grothendieck topos theory, which is developed on the basis of category theory, the science of compositions, and where there is a general form of approximation which contains as very particular case the approximation of real numbers by, for instance, rational numbers or the type of numbers you can really name and store in a machine. But the framework developed by topos theory is incredibly more general. And so for me, it is interesting to try to do something in these terms.
Yes, I fully agree. Based on my limited understanding of your topos theory, I think existing AI theories are still based on preset first order set theory structure, and which are behind the deep learning practice. But I think the future direction, at least over the long run, should be developing mathematics based on toposes. Use a rich structure of topos and explain from the second order how the system learns the first order structure from the zero order, right? That's my humble interpretation of what you say.
No.
And
yes, I wanted to react to the approximation problem.
Yeah.
So indeed, linear superpositions are not sufficient. So we could also mention wavelet analysis, which is perhaps a bit more powerful. It's a time frequency analysis, but it seems it won't.
It's a more flexible dynamic than Fourier.
Somehow, but I think it will fail. And actually, there is a paper in 2016 by Ronan Eldan from Microsoft Research, which is the power of depth. And so he comes up with a function that you can represent with a neural network that is not so big if you allow some depth. However, if you restrict yourself to a depth 2, which is what the classical approximation theorem is about, you need a huge network if it is shallow. So we still do not quite understand the power of depth. So I think it makes the point very clearly. I mean, we would like to have a quantitative understanding of the power of depth, and it seems it's tough, let's say. Maybe one thing I would like to ask is to add, sorry, is that so the power of composition is something indeed we would love to understand. Maybe another ingredient of the success we see is that we don't train neural networks on arbitrary data, and there is a lot of structure in the inputs we consider. The structure is also partly there, and maybe it is also something that we need to spend more energy trying to understand. And I would like to quote a paper that is doing something like that. It's a paper by Ben Arous et al. In 21. It got a an award at New Rips that year. It's called High Dimensional Limit Theorems for SGD, Effective Dynamics and Critical Scaling. So they come up with a notion of an underlying low-dimensional structure that the network is tracking somehow, even though it's much bigger in a higher dimensional space. There is an underlying low-dimensional dynamics, and this might arise because you are training on very specifically structured input data. I think this is also something we need to keep in mind when we try to understand the successes that defy us right now.
And the high-dimensional dynamics, one of your favorite, Professor Moulines.
Yeah, but
anything to add?
Well, we'll add something that I think we are sort of understanding what happened in convolutional neural networks. So because we have this convolutive structure, so it makes sense that we are trying to convolve, so to detect patterns at different levels. There is a hierarchical structure, but okay, now ConvNet, so it's not fully understood. But I think we get some ideas of why it should work, and also what are the relationship with for example, wavelets, especially this idea of trying to have a multi-scale analysis, so you can have details that's fine scale that you aggregate, and then you do with pooling, you go to lower frequency, larger interaction. Okay, so it makes sense. I think we are not very far to understand why it works. But when you go back, you go now to transformers, as I say, it's another story, because there is no transformers are to me much more mysterious, because you have this. They are mysterious because you try to compute something which looks like probabilities, and you redo some kind of very complex computation, because you reintroduce sign with a multilayer perceptron, the output of the transformer, then you redo some kind of correlation. So even though, so it's not only, it's a kind of composition, but which is much more sophisticated than the composition that you do with CNN, in particular because you're trying to find the correlation between points which are far away in the scene. And yes, I think there are, so for example, transformers are very, so CNN to me, we are not, we more or less understand that deep layers are trying to extract features, and you have there is some kind of fully connected layers at the end of the network where you are trying to make a kind of discrimination. So there are even some theory which support that with neural tangent kernel, but now transformers, which are used everywhere, is add an additional level of complexity, and yes, so it's, I think we still have a lot of things to understand. Yeah.
Great. My next question is about diffusion model, therefore directly to Éric Moulines. Diffusion models are gaining increasing attention for their performance in generative tasks. How do you view the advantage of a diffusion model compared to other generative models such as GAN, VAE, or flow-based generation? And also, in future research, what potential do you think diffusion model have that has not yet been fully explored?
Yes, so there are many questions. Okay, so the generative model, the history of generative model started, I would say, the modern history of generative model, because generative model are very old, but modern history started in 10 years ago, basically with the work of Max Welling and Kingma on the variational autoencoders, and about at the same time the work of Benjo and La Rochelle on generative adversarial networks, and others, of course. And these are very powerful. So VAE, it's clear that VAE lacks expressivity, so it's very difficult with VAE to obtain a very high quality image. Even if you can generate complex scene, variational autoencoders fail a little bit to be able to reproduce, for example, a very high quality texture. And okay, so there are caveats. If we go into details, of course, there are some VAE which are able to reproduce that, but which are, for example, VQ VAE are quite good, but they are not at the level of diffusion today. GAN, I think GAN are very appealing. It's appealing because you again are trying to obtain a loss, what is to discriminate between the true and false images. So the idea is very nice. The problem is that it's extremely difficult to learn because you have this type of min-max problem. So because you are willing to learn at the same time a generative model and a discriminator, and the interaction between the two is very, very complex. And in practice, GAN are very well known to be extremely difficult to learn. And so diffusion models, the thing which is surprising, and once again I don't have a clear explanation why, is that the estimation of score is somehow not that difficult compared to GAN, for example. So it's and at the same time, diffusion models are extremely good at generating very, very high quality image, or objects in general, time series and things like that. They are very it's like transformers. It's very universal. You can apply them to a lot of different type of data. Why? Because the estimation of the score seems to be it's not that difficult. At least with you can apply the same type of framework, UNet, with some transformer layers and the structure of this network, and you use basically the same structure for any type of data, and it seems to work well. You can use this type of structure for videos. You can use this type of structure for images. You can use this type of structure for spatio-temporal time series analysis, spatio-temporal data, and things like that. So it's I don't have a clear explanation why, but it works well. Of course, there are many directions of research. I think one of the most interesting direction of research is to go away from classical methods. So what happens if we are trying to learn diffusion type ideas to, for example, text, or there have been some discrete structure graphs, or where for an image or the time series it makes sense to add noise and to denoise the image. But of course, we will not add noise to a text. It doesn't make sense. So you need to do something else. There have been things which have been proposed, and so I think that clearly it's a direction of research. And you have another very interesting direction of research. It's also how to. So one of the main problems with diffusion today, I think, is that they are reasonably easy to train. But inference time is a very big problem. So when you use them to synthesize new objects, it takes a lot of time. So because you typically, in order to obtain high quality image or high quality objects, you need to use a very large number of intermediate steps. And so most likely, in fact, we have to do, like was mentioned by Laurent before, we need to do a kind of distillation. You mentioned that also. So you need to distillate this model into a much simpler model. And also that's also a mystery of deep learning. So for example, you can use GAN. So you will take data, you will learn a diffusion model, and then from this diffusion model, in a kind of teacher-student approach, you can distillate this diffusion model into GAN, and that will work better than to learn GAN from the data itself. So it's a bit surprising, but for sure it will work like that. So I think that's another direction of research. And of course, the theory of diffusion model is very widely open, because it's from a statistics point of view. It's difficult to understand why the estimation of score is easy, whereas apparently it's reasonably easy, whereas estimation of density seems to be complicated. At least theory says that the estimation of density is complicated. So it's difficult to understand why. So there are possible directions of research there. So for example, how to test what is called the manifold assumption, which is a manifold assumption is that you have a very low dimensional structure which is behind the scene, and that is captured by the score, and which is not so easy to capture by the density. But it's something which needs to be really discussed. It's not clear. I believe also that there are a lot of things to do to apply diffusion model to other problems. Like for example, one problem which is very interesting to me is a conditional diffusion model.
Yeah.
When you are willing to, for example, sample conditionally two objects, and there are many situations where you have two objects, x and y. You have a lot of unconditional example of x, so you can get very good representation of x. You have lot of representation of Y, and you have good generative model for Y, and you don't have much per object. It's a case, for example, when you do a prompt to image. So you have a lot of text, so it's easy to have a very good generative model for text. You have a lot of images, but you make very good generative model for images, but there are not much paired examples, so caption text with the image which has been captioned when you have to learn then so I think this is and I have many examples like that. So and also that would be very interesting to understand how you can combine. You have very good generative model for X, very good generative model for Y. You don't have so much paired examples, so you don't have so much example of the conditional distribution of X given Y, and now you can learn that efficiently. I think it's also so there are many directions of research, both practical and theoretical.
Yes, I fully agree.
The theory is not. I think for the time being, the theory is not understood at all. So the only thing which is understood is very simple examples, like for example, you are willing to approximate strongly convex potential and things like that. So log concave, strictly log concave distributions, and you can do calculation. And yes, so that is known. But as soon as you go to practical example, I think the theories that we have now, as I say in maths, a good theory should. So a good theory should give you hints to go further. Okay, so and right now all the theories that we have, you say okay that it works and it is plausible that it works on very simple scenarios. So this is not a good theory to me. It's like okay, so it's a confirmation you develop, you discover something in practice, and you say okay on a very simple example it seems to be okay, but it's not a theory that allows to go further to say okay no, it's not exactly diffusion that you should use. You should do that, and we are not at this level. And this is why also the diffusion, the theory about this type of structure, the diffusion model need to be, we need to understand more in order to go further.
Sure. Yeah, because diffusion model has a more stable random process, forwards and backward, and also can be conditioned, therefore becoming more interpretable and controllable compared to GAN and other type of
I think that it is very robust. The thing which is very robust is that the problem to learn is really a denoising problem. So so this is a kind of problem which is very well formulated, and where in fact the learning is efficient. So you try to learn. You take an image, you take a noisy version of this image, and you want to denoise it. So it's easy. It's an easy problem for DeepNet. So I think that's part of the success. Whereas GANs, when you have tried to even spectral GANs, which are not extremely complex, are extremely unstable to learn. So it's known, and diffusion it's really so you can learn on simple image data set. Learning a diffusion model is very simple. This is part of the success, and also and it's robust and you. There is no special super. Of course, there are some tricks, but there are not. It's not like a very large number of tricks in order to be able to develop a good generative model.
Yeah, image space is continuous. Is relative easy for diffusion model, but if we apply diffusion model on drug discovery or material science, the space is actually discrete, right? And we need to find many tricks how to work around.
Yes, I think that of course in that direction, I think there are many things to do, and the way to start from a distribution to go to another distribution is very important. The noise, the way you will, the equivalent of the noising process, which is quite obvious for I would say images or time series or something like that, you need to change it because it's a discrete structure. So you need to make a process which is so for this structure, I think it's the direction of research. There are already so I know that I never work on that, but I know that diffusion model, what we call diffusion model. So something which looks like diffusion model is efficient for text. Okay.
Yeah.
It has been very efficient also for text-to-speech synthesis. For example, they use diffusion model. It's extremely good. And okay, so to me, it's clear that the idea of diffusion model can be carried over to other structure. Okay, I think perhaps text, perhaps graphs. I don't know, but then you need to design the right noising process, and also that the task, the denoising task, should be also more or less adapted to this. So they need to be. We need to think about that. And there are already works on that, and promising work, by the way.
Laurent, Massoulié, can we also combine diffusion model with, for example, probabilistic graphical model?
So we can imagine some noising processes adapted to discrete structures such as graphs. So local rewirings come to mind, and you could really have this process which takes as an input a connected graph, and you do local flips. You'll converge to something that is a Merge-friendly graph conditioned on being connected and having that many edges. So this would be the natural noising process, and so you may then come up with a backwards process.
There are some tricks, right?
I think this might be considered definitely. One thing that I wanted to say in reaction to Eric's points, and he's already made that point somehow. It's funny that people in signal processing have been studying for a long time how to denoise noisy objects, but they were focusing on the estimation part and not so much on synthesizing samples from the posterior distribution of the input. And that is what diffusion models are all about. So we want to sample, and the experts in signal processing had all the mastery of the mathematical formalism to attack that, but they did not have the question, and so the question came from outside, and so people started generating images, and so it's interesting how you have cross-fertilization, and now the expertise of signal processing can be brought to bear, and score functions are the right notion that we need to estimate in order to have the correct diffusion model, the backward process. But the history of how it comes to be is not a linear one. I mean, it goes back and forth between communities.
I know, and estimation, let's say, based on posterior, is always a little bit stable, right? Laurent, anything to add?
Yeah, I think that this story of the theme of diffusion is extremely interesting, quite fascinating, in fact. And it is a perfect illustration of how, in mathematics, for some particular reasons, a new theme may appear somewhere and then spread to very far away domains. So here, the name diffusion model tells us where it does come from. It comes from thermodynamics, of course. It comes from the heat equation. This is heat. First, the name diffusion of what? Diffusion of heat. Yeah. For instance, suppose that in a room you have some source of heat somewhere, and then this heat will gradually spread to the wall of the room. So there is an equation for describing this, for modelizing this phenomenon. This is the heat equation, where of course the central ingredient is the so-called Laplacian. Yep, okay, yep. And this is the birthplace of diffusion models. And something very fascinating is that it has spread this idea, in particular, this central ingredient, the Laplacian, has spread to very far away domains of mathematics. So, for instance, as of course, somebody coming from pure mathematics, I am familiar with so-called Hodge theory. So Hodge theory consists in proving that in many geometric contexts, so-called cohomology classes can be represented by so-called harmonic functions, which are defined by the Laplacian. So the consideration of Laplacian and the kernel of the Laplacian singles out particular functions on particular differential forms, which allow to represent cohomology classes, which is an extremely abstract topological invariant. So this is an instance of, you see, coming from the heat equation, there was this most important development in geometry. And it is not at all the end of the story. In fact, just 10 days ago, we had a very big conference on topos theory, and one of the talks, in fact, a really magnificent talk, was about the phenomenon of diffusion in the context of so-called presheaves and sheaves. Because then, in this context, you can define some forms of Laplacian, so always the same ingredient, and these Laplacians may be linear, just as in the classical situation, also in the case of diffusion models as they are used in the type of AI Éric was talking about. But you can also develop some kind of combinatorial Laplacians, which only require an order structure, and all these forms of Laplacians always do the same thing, which is just by iteration, which means following an evolution, gradually approximating an equilibrium state, which, for instance, in the case which was studied in these talks, this equilibrium just meant gathering partial information. For instance, suppose you have different sensors, you have cameras, you have so you get different partial information, and you want to create a global picture out of these partial informations, which would be coherent. And the way to combine the partial information in order to get a coherent global picture, something where all the partial informations are put together without contradiction. So the way to obtain that in this talk we had 10 years ago was through a diffusion process. So it is completely different from the diffusion models which Éric was talking about, but except for the fact that there is a diffusion process. So this means that here we have a very important theme of mathematics, which was born in a particular situation, the heat equation. So it was discovered by physicists, and it has spread in many domains of mathematics, and it is completely clear that the story is not ending. So this theory of diffusion has still to develop.
Yes, that sounds very exciting, astonishing. I think we can apply the diffusion idea on among different mathematic domains.
Yes.
Right. Let's say in many problems we can find isomorphism and invariance and equivariance among different mathematics domains, and if this exists, then of course we can apply diffusion, right?
Yeah, and so this theme is most important. And you see, talking about the Laplacian, of course, in history, another extremely important development was the introduction by Dirac of the square root of the Laplacian. So, okay, so this is yet another development. You see, all this is an illustration of the creative power of mathematics. From a very, you see, the Laplacian in a classical situation is extremely simple to define, but out of that, in fact, many new directions of mathematics and physics were progressively born.
Yeah, that's a real amazing part of mathematics research. So my next question is to Laurent Massoulié. It's about your domain, a graphical model. Recent years have seen many advances in graphical models, such as a stochastic block model and Erdos-Renyi model. However, these probabilistic graphical models are far removed from the real-world graphical model, as normal people know. And how should graphical models be extended to better suit practical applications. Additionally, while studying graphical models, we often analyze the information theoretical threshold, but in real-world application of graphical models, these non-polynomial algorithms are difficult to implement. And what is the practical significance of researching the IT threshold?
Thank you. So indeed, we have spent a lot of time studying those very stylized models. Stochastic block models are random graphs where you have a partition that is a starting point, that's the signal you're looking for, but then you don't observe that directly, you just observe a random graph with more edges within a block than across blocks. And so a lot of work has been dedicated to identifying IT thresholds as well as computational thresholds for these. And spectral methods seem to be the most efficient approaches for and so the Laplacian has been studied a lot, the graph Laplacian. And it turns out we came up, so physicists came up with a linearization of the so-called Bethe free energy that gives you a more intricate matrix associated to a graph, which is an edge-to-edge matrix, so it's broader. It's called the non-backtracking matrix. And this has a spectrum that denoises the most efficiently possible your graph. So for those stochastic block models, indeed, this is the best you can do. And this is a matrix, the non-backtracking matrix that was introduced by number theorists, completely unexpected relation. So indeed, the stochastic block model is way removed from real graphs on which we want to do clustering. So perhaps an easy way out is to say, nevertheless, spectral methods based on this non-backtracking matrix seem to perform quite well on data that is not at all sampled from those stochastic block models. We have experimented with that, so data coming from social networks, which really are far remote from stochastic block models. So maybe there is some underlying genericity that we have not understood, which would justify a posteriori our focus. But somehow that is, to some extent we have shown that. So we went beyond the classical stochastic block model. We introduced some other characteristics that are always seen in real graphs, which are power law distribution for the degrees. If you look at, the numbers of contacts people have on the social networks, you have those with 1 million contacts, and then you have this power law decay as you plot the number of contacts. If you modify your stochastic block model to capture this feature, still the non-backtracking matrix is able to do as best as you can hope for. So to some extent there is this genericity. But then to go beyond, maybe some other approaches, so maybe we can get away with the probabilistic modeling of graphs and go perhaps more towards extremal graph theory and take a completely different look at the problem, and that will be different mathematics altogether. So this is something I think is very promising. It seems very hard though, but somehow there are things that you see on a probabilistic setup, and you see them without. In practice, this seems to hold without the probabilistic assumption. So it seems to be, like an unreasonable efficiency of probabilistic modeling. And it would be very interesting to understand that, why that might happen. And I think extremal graph theory might give you another kind of answer to that. You can say, I'm taking a graph with those prescribed properties, and then I want this graph to have the most extreme behavior with respect to another metric. And maybe all that you have predicted on random models will carry over on extremal models. And I think what we see in real life, they tend to be extremal structures. Something gets optimized, maybe you don't know what, but you tend to see many optimal structures. So the random models are not like that, but maybe they share the same properties. So that's fine.
Okay. Anything to add?
No, so here, in fact, the example of graphs is also an illustration of a quite usual phenomenon in mathematics, which is that most of the real problems we would want to solve can be phrased in quite elementary terms or completely elementary terms. So for instance, the comparison to understand whether two graphs are equivalent or not exactly equivalent or very close. So this is an elementary question. But mathematical experience is that when you try to answer an elementary question, either it is trivial or it is extremely difficult. And what mathematicians try to do when they face a question phrased in elementary terms, which is extremely difficult, is to embed this question in a more sophisticated theory. And so, okay, this is, it's absent, it was, your talk was an illustration of that, and but it is a very common phenomenon in mathematics, that, yeah.
Okay, let's move to the next question. So far, we have been talking about the structure of deep learning and also the relationship between structure and performance. Now, the next question is about given a structure, and how can we train this structure most efficiently? The current paradigm involves first defining a performance measure, that is a loss function, then selecting a function from a candidate function set, and that best approximate the true relationship between the input and output spaces in an every sense. Everybody knows that. And this approach, where natural, is predicated on some assumptions that performance measure loss function is independent of the data distribution, and also the training data is abundant, broadly representative, meaning the foundation is actually loss of a large number, right? And also actually the data, all the data are accurately labeled, and that the regularization terms introduced in this log function are often empirical designed. And in practical applications, these assumptions are often violated or unreasonable. How can we overcome these prior assumptions to improve the performance of current deep learning algorithms? Eric?
Yes, so it's a very complex question. So there are several questions to the same question. So the first is about data. So I think there are techniques which have been proposed, and generative model might play a role there. It is well known that training data is often scarce, and of course training data may be not representative in the sense that, for example, some instances are not well covered. You might have also data with inaccurate labels, which happens very often in application, where the labeling sometimes contains some error, especially if it has been done by kind of cooperative labels. And so for such situation, it's a good idea to use data augmentation to artificially increase the size and the diversity of the data set. When the real-world data is limited or is very difficult to collect or is very costly, of course, we can consider to use a generative model, like, for example, GANs or diffusion model, to try to enrich your data with novel instance. Another way to attack the problem of data scarcity is about self-supervised learning. So So the assumption that abundant data and well-labeled data is available is often unrealistic, and self-supervised learning, which have been very powerful, show very powerful structure, is to try to leverage the structure of the data itself to create what is called pseudo-label, which can train model without having to require a large amount of data. And LLM are an example of that. So LLM is all about self-supervised learning, and it's the same for image. You can in image processing you can feature extraction for image is mostly done by using self-supervised learning. So there are also more classical way to tackle the problem of data scarcity, which is about domain adaptation and transfer learning. As I said, training data may not always be broadly representative of real-world data set, and transfer learning or domain adaptation can help to leverage pre-trained models from related tasks or domains to improve the performance in the target domain with much less data. So it's another. And so considering to finish adaptive and task-specific loss functions, or as I completely agree that loss functions are often very empirical, and that's a kind of expertise of engineers and people which are designing the loss function, and sometimes the loss function might not fully capture the complexity of the task. And of course, there are a lot of work recently which have been devoted to that instead of using predefined loss function, people try to learn adaptive loss function that can be employed. And one way to do that is to use meta-learning approaches, which allows the model to learn the loss function itself based on the task, and which apparently leads to more effective optimization. Finally, there have been some work recently also on robustness to data distribution shifts. This is a very well-known problem that the assumption that the performance measure, the loss function, is independent of the data distribution is often violated. And to do this, of course, you can use one way to do that is also that it's a big field, is to use distributionally robust optimization to optimize the model for worst-case scenario rather than average performance, and to make the model more robust to distributional shifts. So you might also use regularization technique like adversarial training, or you might add noise somehow to training data, which can also improve the robustness to out-of-distribution data.
Yes, you almost mentioned all the points currently we have. I just want to add one more point to theory-based regularization. Actually, nowadays people are doing regularization empirically, right? And but from more mathematical point of view, let's say looking at for the most simple example, L1 and L2 regularization, there are different angles of understanding how it works. For example, from Lagrangian multiplier method, and also from weight decay, and also from the point of view of Bayesian formulas, as well as even from the point of view of VC dimensions. Right? There are many ways of explaining why regularization works. And anything to add?
Yeah, so here a remark which can be made on this deep learning process is that it is based on extremely simple mathematical principles. Yeah. So first, of course, there is the idea of constructing functions by composition. So in practice, most of the time, you just compose linear functions whose matrix coefficients are allowed to vary. Alternatively, with nonlinear functions which are fixed. Okay, so in this way, you have big families of functions which allow you to approximate data. So you suppose you have, of course, you need big data, and you will try to construct a composite function which will approximate as well as possible a set of data which you will introduce as input. And of course, in order to measure how good is the approximation, you need a loss function. Yeah. Okay, and what you do is just to differentiate the loss function with respect to the varying coefficients of the linear factors in the composition. So this means, what do you use? You use the idea of approximation, the idea of composition, and the basics of differential calculus. Okay, with the idea that you will improve your approximation just by moving your parameters in the direction indicated by the gradient you compute, just by differentiation. So the mathematics principles are extremely simple. It is really amazing that it works so well. And of course, it is based, it can work when you train the system with huge data. So I understand, for instance, that for large language models, the most advanced systems basically use as data all existing text. So this means that the amount of data cannot increase because here there is a limit. Okay, and here, of course, a remark which can be made is that this type of deep learning has nothing to do with the way our mind works, because we don't work with big data. Okay, we are able to learn from few instances. So, for instance, just by training with big data, we are able to teach a system to recognize whether an image contains a cat or does not. Okay, but for that you need a training with hundreds of thousands of millions of images. Okay, but a child will learn to recognize a cat just if you show to him 2 cats, and so this means it is completely different. And so here, of course, this is the fact that the use, so statistics has become a most important part of mathematics. It has become very powerful, but for our human mind, statistics is something very strange and really alien to the way we usually think. And how do we think? Quite often we think by deduction. So deduction means that we have a general idea and we just apply this general idea in a particular context. So this means it is instantiation. Okay, so for instance, the paradigm of that is the sentence, all human beings are mortal. Socrates is a human being, so Socrates is mortal. Okay, so this was known 2,500 years ago. So we are able to do deductions. But most of the time, our mind, even though it is able to make deductions, doesn't work in this way. In fact, for us, we are able to do that, but it is not the most natural way we think. And I think this is the reason why mathematics is so difficult for most people, including for us, by the way. So it is not easy to do mathematics, which is when you write a paper or something, you have to make deductions, but it is not so natural for us. And it is why it is difficult, even for mathematicians, to write mathematics. For us, what is most natural is to make induction. Induction means just to be confronted with instances and to infer from that more general knowledge. And in fact, I am particularly interested in trying to develop models, mathematical models, and possibly machine implementation models for inductive reasoning. By the way, I think there is a relation here with diffusion. Because, you see, what is diffusion? For instance, you have a heat source and it spreads gradually to the whole room. This is diffusion. But there is an analogy here with induction. You have your mind sees the world in a certain way, and you are confronted with a new instance of something, and this new piece of information, in some sense, will spread in your general picture of the world. So here, for me, diffusion is, there is a relationship between diffusion and induction as a way of thinking. But I am also interested in other models. In particular, I see topos theory as a mathematical theory which provides a model for inductive reasoning. But in fact, it is precisely for that reason, it is not a surprise that, as I explained, as I said a few minutes ago, just 10 days ago, we had a talk about diffusion models in the context of sheaves, which means in the context of topos theory.
Yeah.
So.
Yes, this leads directly to my next question is about understanding the logic and also causality. And actually looking at what you have today for AI, the whole mathematical framework is still, let's say, starting from the very basic foundation like cumulative distribution function and the probability density function, and then we move up to things like joint probability, conditional probability, marginal probability, and then we introduce a random variable. With the variable, we enter into the space like probability theory, statistical learning, and information theory. I think with information theory, we are already facing I already see some ceiling. I think we need new mathematics in terms of understanding the logic, and also even generating new logic. I mean composition of a new logic, and with this logic we can create new functions, as well as understanding the causal relationship, because I think the biggest bug today is still all the algorithms are still based on a correlation, but the basic assumption is IID, and this is a controversial, right? And we never, using today's mathematical tools, we can never precisely model the correlation like between entities, right? We always take the most easiest way, but I mean the independent distribution, this is actually not the reality. So therefore, my first question is, let's say to you, do you have any idea how can we develop AI into the age of able to understand logic and causal relationship?
It's a very hard question. I'm not sure I have a good answer to that. About causal reasoning, there have been some theories. So I guess the one by Julia Pearl is the one that comes to mind, where you need to introduce counterfactual action in order to distinguish causality from correlation. But it's not perhaps a workable theory in many cases.
To heavy computation.
Yes, it's somehow there are other attempts to develop a more practical theory. There's this notion of Granger causality that comes from economics, and this is much more workable somehow. And so people are actively developing this way of assessing causal relationships, and so I guess this is the one I'm aware of that seems promising, but it's not logic, so it's a very limited part of what you're asking. So as for a general I think some aspects of logic can be developed. So, you know, there is this stance by Yann Lequin, who's at Meta. He keeps on criticizing LLMs, saying they cannot plan, and the real AI should be able to plan, and this is what we need to target. So I think adding some planning capacities to current AI systems is limited kind of reasoning, where you have temporal limitations, dependencies, where you, if you want to plan a trip, you need to have prerequisites. So there are some basic subsets of logic, like having a you know, directed acyclic graph of dependencies that need to be processed. I think this is reasonably easy to add to the current tools of AI. So some limited subsets of logic we can consider easily, but I think this is the way forward, actually, to identify those limited subsets and have augmentations of current systems with those restricted logics that are reasonably easy for experts in AI systems to force into the existing systems. So that would be my answer.
Eric?
So for causality, I'm not an expert, but of course it's a topic which is very, very hot in statistics. I would say like half of the statisticians today are working on causal inference. It's a very, very big topic, especially from observational data. So of course, I think the causal inference is understood when you can do counterfactual action, so that when you have observational data, you don't have counterfactual action. So then trying to discriminate between correlation and causality, it's very big. It's very important in many topics, and I say 50% of statistics is about causal inference today. For logic, I have no clue, but I will say that. So yes, I know that Yann Lequin is speaking a lot about that you cannot do anything with autoregressive model because they don't do planning at the same time. When all the example I had for LLM. You can write a perfectly coherent text of 4 pages, which start with the introduction and which end up with the conclusion. So I think that yes, even if they show some planning, and also for the last model of OpenAI 01 is clearly doing some kind of reasoning with. It's not clear what they are doing, by the way, because they never. They never really. Released even the idea of what they are doing, but clearly there is a kind of chain of thought which is behind the scene, which most likely use their model to generate answers, and then from this model you generate new questions, and these questions are most likely there is a way of reasoning, and they are considering several paths, but it's difficult to understand exactly what they do. But I think that perhaps with the solution, my feeling after I'm working on machine learning for 45 years, not in statistics and machine learning, so globally, and ideas which seems in general sensible does not work. So you should try things which are very, very insane that might work, you know. So if you remember the basics of AI when I was very young, so it was in the beginning of the 80s, everyone was about expert systems, and I was doing speech recognition. I was in a lab where we were developing one of the biggest speech recognition system. It was in France, but it was a very, very big lab. And you have a lot of phoneticians where we were looking at sonograms, and they were formulating very clever, they know very well sonograms, and they were formulating a lot of very interesting set of rules. It never works. It was the same for machine translation. So I remember there was a big lab in France called JETA, and also in CEA. So what they do was perfectly fine. They do, you start from text, you did syntax, local syntax, global syntax, semantics, and you translate to a pivot language and you do synthesis perfectly fine, never works. And whereas the technique where you do LSTM and sequence-to-sequence modeling and a lot of stat works. So I think, yes, and Jan was strongly pushing for this type of solution. So his late idea that you should have a kind of planning and reasoning is a bit, for me, surprising because it's an idea which makes sense, of course. But in AI, typically, it's not necessarily ideas which make sense, which are lead you to success. Okay, so that's it.
Laurent, you must have your very unique view.
Yeah, no, in fact, I have become very interested in logic ever since I learned that logic and geometry are related and in some sense become equivalent one to the other through quadratic opposites. Before, as most mathematicians, I had I was distant from logic and I had a priori thoughts about logic. I had never learned formally logic, and I thought that as a mathematician I didn't need to study it. Especially in France, it is like that. But then I became interested into logic when I understood that in fact it is just a different way to look at geometry thanks to topos theory. Only topos theory provides such a bridge between geometry and logic. And then I became interested in this way into logic, and this made me also more interested in computers. Because, of course, computers by nature are logical machines, more than number processing machines. And in fact, it is a little awkward, it seems a little awkward for me that machines are used mainly to process numbers, vectors, approximation of functions. Of course, they can do this, but it seems to me that it is a little artificial if we remember that by nature they are more logical machines. Okay, so this means that in some sense I am expecting that in the development of computing power, in the development of the use of machines, gradually wider horizons will open, which means people will learn gradually to use more possibilities of these machines. I have so my personal feeling is that presently machines are used in very particular directions, and other possible directions are just not seen at all. So this is just because of the weight of history and also the weight of education. In fact, most computer scientists, of course, have some background in mathematics, but their background is primarily in calculus. Yeah. And it is natural when you want to use machines to try to implement models you know. And so it is dependent on the type of education you got. And so this means that in fact, I think that the education, the mathematical education of students, especially of future computer scientists, should be more open. Not only dominated by calculus, but with other points of view. So, for instance, your lecture was about graphs. So this is also, you see, it is not differential calculus, but it is also mathematics. And so here for this conference, we have many students coming mainly from China. And I was pleased to see that, in fact, all of them know the basics of category theory. Of course, they also know calculus, but they all know the basics of category theory, which for me is just as important. And it means that the future generation, especially of computer scientists, will be able to imagine more directions. And if you are not able to imagine them, of course, you will not develop them. So it is good to open avenues with a broader education. Another thing, so here you see I am advocating logic, mathematical logic, especially in its relationship with computers. But as I said a few minutes ago, so of course logic has to do with deductions. In some sense it is a science of deductions. We are able to do deductions, but it is not the most natural way of thinking for us. And it seems to me that the most natural way of thinking is induction. Yeah. And here I am especially interested in the equivalence of, on the one hand, first order logic, with dominated, of course, by deductions, and on the other hand, the process of generation of Grothendieck topologies, which I would want to call topological reasoning, which is different from deductive reasoning. Yeah. But in fact, there is in fact a combination of theorems, which I in fact stated quickly in my talk this morning. So a theorem by Grothendieck and a theorem by Olivia Caramello, which tell us that these two forms of mathematical processes, so deductions in first order logic on the one hand, and generation of Grothendieck topologies on the other hand, in fact are constructively equivalent. And so this for me is a fascinating direction to explore. And in fact, I think that the way our mind works is more topological than deductive. And so, in fact, I am dreaming that we could use machines in order to implement some kind of topological reasoning which would be much more alike the way we think.
Okay, this leads to my last question. It's a very different question because all of you are excellent French mathematicians. As you know, Paris has maybe the biggest concentration of excellent mathematicians. And but looking at China, China indeed invests heavily in the education of talents in mathematics. And China has also great ambition to excel in mathematics. And for example, you have been involved in two countries' education system in mathematics. What's the difference in education system in mathematics? And what's your suggestion to the university in China in the mathematics area?
Yeah, this is a question for me.
Yeah, we have discussed a few rounds. So I know what you might want to say, but I think your opinions are very valuable. I want you to share your opinion with all the audience.
Yeah, so of course I have an experience of traveling to China many times, and I am, at least officially, one of the heads of a joint program between China and France, specifically at USTC University in Hefei. And this program consists in selecting very bright students in order to teach them mathematics in the French way. And not only in the French way, but even in the French language. So this means that first they have to learn French, so they do in just 1 year. So it is really incredible because they arrive in this university as a first-year student. They have all the teaching lectures in mathematics, in physics, in experimental physics, so it is already a huge amount of work. And in addition to that, they have 10 hours per week of French language. And after 1 year, they have to master French because beginning in the second year, all their lectures in mathematics will be in French, given by French professors, in order to teach them mathematics in the French way. Of course, it is just...
Could you please be more specific in French way of mathematics education compared to what you know from China?
Yeah, so
what's the difference?
They are supposed to... in fact, the French professors teach them following the math program of so-called class préparatoire, which are the elite education system in France. So this means that, you see, maybe the differences between the way Chinese students are usually taught is that it is less focused on problem solving, more about learning theories. You see, on the type of problems, the type, the organization is different. Okay, so in fact, it is important to realize that on the one hand, of course, mathematics is universal. Okay, and we all have this experience that as mathematicians, we know mathematicians from all over the world, and of course, we are able to understand each other. So it is very nice when you are a mathematician. You can travel to many countries, and you are welcomed by other mathematicians. So it is the experience of scientists, in particular of mathematicians. So this is certainly true. But it is also true that in history, different countries have developed slightly different ways of doing mathematics. So certainly there is the French way. There also was a German way. There was, or there still is, the Russian way, which I especially like, by the way. So why is it like that? It is like that because I think mathematics is not cut from culture. And I think that the relationship between mathematics and culture is very deep. And so, for instance, we have to remember that when we write mathematics, what we write is mainly a text. In some sense, I see mathematics as a part of literature. You see, so no, but it is very important, and in fact, it was especially important in the work of my most unnamed mathematician, Grothendieck. If you look at the huge work of Grothendieck, there are no formulas, there are no computations, even though, of course, the Grothendieck mathematics make possible many new types of computations. This is almost only text together with some diagrams which are very telling by themselves. And so especially, in fact, Grothendieck did not even consider himself firstly as a mathematician. He considered himself firstly as a writer, who, because of the circumstances of life, happened to do mathematics. But he was mostly a writer. And in fact, when he was an high school student, his fellow friends and teachers had given him a surname. The surname was not the mathematician, it was the poet. And you can see, when you learn his mathematics, you can see that it is dominated, it is inspired by his extremely deep relation with language.
Yeah.
So, in fact, not only one language, several languages, because his native language was German. Then he came to France at age 11. He learned French, so quite late. But in fact, he became a master of French language. And his mathematics is based on that, on his strong relationship with language. So here I give the example of Grothendieck, but you can give other examples. So for instance, I mentioned Blaise Pascal, who is in some sense one of the fathers, or maybe the father of statistics, the first father of statistics. But Blaise Pascal, of course, was also a philosopher, and as a writer, you can consider him also as the father of modern French. Okay, so this is an instance, but I could give many others. And in fact, it is important to remember that in the history of mathematics and science, in especially, for instance, in European countries in the last centuries, up to the mid-20th century, in fact, usually scientists had been educated firstly through classical studies, which mean Latin, Greek, philosophy. Only lately they came to mathematics or physics and so on. And in fact, I think that today we miss that. Mathematicians have become, in some sense, they don't have, most of them don't have anymore this classical education. And the result is that they become a little more like technicians. And so this means that they don't see mathematics or science anymore as a type of thought. And so, in fact, I would wish some renewal of classical studying. And of course, I wish that for France, I wish that for European countries, but it also has to be said that this, of course, also exists in China, because China is a great literature country. For China, poetry is extremely important. So it is present in the Chinese tradition. And so something I often say to young Chinese students is that it is important for them to learn not only mathematics, and especially their relationship to this legacy of centuries, even millennia of Chinese literature is very important. And in fact, I would expect, for instance, I am dreaming of the new development of Chinese, specifically Chinese school of mathematics, which would be deeply inspired by Chinese literature. Just as French mathematics has been, in fact, inspired by the deep education in French literature and classical literature for centuries of French mathematicians. So this is something I regularly say to Chinese students. It is important for you to be not only mathematicians.
Yeah, very impressed talk. And anything to add to conclude today's conversation?
I'll just add that I'm very sensitive to what you said. I spent 8 years in Cambridge in the UK, and I thought the mathematical writing there was much more literary than the one of my master's in France. That the English way would be to write a paragraph which would be much more powerful than a dry series of deductions. So, but okay, so there must be an English style as well. And,
yeah, for sure,
mm-hmm.
for sure.
Okay, I think thank you all for your very insightful and enlightening talk. Thank you.
Thank you.
Thanks.